Morning, everyone. So far in this chapter, we've been looking at reaction kinetics. Essentially, some reactions occur really quickly, some reactions occur really slowly. We wanted to figure out at first, how do I measure the rate? What are some physical characteristics like mass change, color change, acidity change? If I can track any change in amount, we saw that by dividing it by time, it can actually give you a measure of the rate itself. Yesterday, we introduced the most important theory called collision theory, and essentially it told us particles need to interact with each other. They can't be in two separate containers. And for a collision to actually be successful, for reactants to actually have any chance of actually forming products, we saw that they actually needed to have two conditions. So let's just start off from there here with our warm-up question. I want you to state from collision theory, state the two conditions for a reaction to occur. Another way of saying that reaction to occur is for a successful collision. So yes, it's sort of under the implication that yes, they have to collide, they have to interact. But what two features? There's a lot of collisions, they just collide, they just bounce off each other, no reaction. What are the two features that we need? And then once you do that, I want you to use that collision theory. So using collision theory, meaning you're going to use those two features. Using collision theory, explain why reactions are slower at colder temperatures and let's say lower pressures. Okay. So again, I'd encourage you just to pause the video, see how you do for yourself. When you come back, you can check your work here. All right. So the two conditions that we need for a successful collision. Again, they've already noted to you there has to be collision, right? So you don't need to emphasize that part. But as a collision is going to happen, sort of one particle is sort of running into another particle, a lot of times they just bounce off each other, no reaction. I need to make sure that these two particles here have the following two criteria. The first one here is a sufficient energy argument. We'll study this in a little more detail in today's lesson here. What is this activation barrier? Basically, there is some requirement for whatever bonds needing to break, whatever bonds needing to form, the particles had to be coming in moving fast enough. If they're not moving fast enough here, they can't get over that energy barrier here, they're not going to actually be able to react. So sufficient energy, I'm going to make that note there again. It needs to be able to overcome what's known as the activation barrier. There's always an energy hill that they need to surmount to get over. The other one here is always a favorable geometry argument. So especially as whichever bonds need to break, whichever bonds need to form, it'd be nice if the atoms are already in close vicinity that electrons don't need to actually jump that far. So favorable geometry here, you can also refer to this as the orientation, the angle of hit, right? So many different ways of saying that part. Those are the two features that can explain what reaction rate actually depends on, right? So now noticing in this question here, they do emphasize using collision theory. So you can't just say, oh, I just memorize it. Colder is slower and lower pressure is slower. I can't just do that because I didn't mention collision theory. Specifically, I want to mention, did I do anything to the energy argument? Did I do anything to the geometry argument? All right. So in the first sort of container here, I have a cold container. Right. So even if I have a gas in this container here, right, still has enough energy to spread out through the container. If I have a container that is relatively cold, what does that tell you about the average energy that the particles have? For a colder system, I know I'm actually going to have slower particles. Right? Slower particles actually imply they start off with lower kinetic energy. Kinetic energy was this moving energy here. I don't have a lot of it. Right? So what have I done? Well, now I have less energy. Now less particles are actually going to have enough energy, right? If I have two really sluggish moving molecules, they always like asking this question as well. As particles approach each other, particles or reactants, particles slow down upon approach when they actually come towards each other. If you look back at yesterday's lesson, that was because of the repulsion. The first thing that encounters each other here is the electrons on one side encounter the electrons on the other. Like charges hate each other here. Again, even though they want to repel away from each other, it doesn't mean they just stop dead in their tracks. Because I already had such velocity coming towards, it's just going to take a little while, but overall, it's actually just going to slow down. In this case here, for you to slow down, that means I lose kinetic energy. My question from yesterday is, where did that kinetic energy go? I had to have traded that kinetic energy into potential energy. Imagine you have two bank accounts here, one called kinetic, one called potential. The total amount of money that you have is always the same, but as you transfer away from kinetic, it's going to actually climb the potential energy account. We're going to study this as a potential energy diagram in today's lesson here. So we have our PE diagram. We can plot it against time, or we're going to see we can plot it against reaction as well. So our reactants had some amount of energy, our products need to get up to some amount of energy, and there is this energy hill for all reactions. What's happening here is, because I was really slow to begin with, I didn't have a lot of kinetic energy trade in. It's like I only had maybe $10. At maximum, I trade the $10 over to potential. So I start climbing, right? I start slowing down. I trade the $10 in. I trade it up for the potential, and I only get partway up the hill. I needed way more energy to actually get a chance to actually form products. I've now hit. I have now the maximum amount in the potential energy count. What would end up happening there? You would say in this situation, we have what's called an unsuccessful collision, right? It didn't happen. Right? The reaction did not occur, the bonds did not break. So for after an unsuccessful collision, the particles would now be really close together. It's that very same electron repulsion. Now that they're actually leaving each other, now that they're actually pushing away from each other, that repulsion will give it that added push here. Oh, great. Finally, we're actually leaving each other here. Finally, we're actually repelling away from each other. It's actually going to speed you back up. It's actually going to try to increase the speed. Well, where did that increase in speed come from? That's sort of like trading your potential. You didn't have much of it to begin with. You stored all of it, you tried to climb it, no luck, and then you just trade that potential back into kinetic so that these particles here can start zipping away from each other, right? So because I'm at a cold condition here, I don't have a lot of particles having enough energy. I can actually resketch that diagram for a successful collision. The only difference, for a successful collision here, we may be at a hotter temperature. We may have particles with a lot of kinetic energy. Even though the particles on the collision course here are going to still slow down, they're still going to trade in kinetic for potential, but because they were so fast to begin with, by the time they store out the potential, they get all the way up to the top of the hill. There's a very special molecule called the activated complex at the top here, but it was just a sheer nature of I had a lot of moving energy to begin with, I can surmount this hill here, and therefore I can react. As the products get formed and they leave each other, we're going to trade some of that potential back for kinetic. Everything else is the same. It's just my starting amount. If I'm cold, I don't actually have a lot of energy. There's not enough particles with enough energy. So there's your first answer. Why is it slower at a colder temperature? We have not many particles with sufficient energy. The particles were too sluggish, and therefore they're not really going to react really well. How about lower pressures? At lower pressure, I always think of pressure sort of opposite of volume. Well, if I have decreased the pressure, what I've done is I've increased the volume. So imagine taking my container like this, it's already cold to begin with, and imagine now just spreading out that balloon, spreading out the container here. Just the sheer act of actually spreading out the container, I have not changed the temperature. We might still be at the same cold temperatures before. The sluggishness, the amount of speed that I'm traveling is still going to be very similar. However, what I've done here, now that we're in such a big container, the chances of you even meeting, the chances of you actually colliding is going to be a lot less. So for that feature here for lower pressure, you can say because we're in a bigger container, there are actually less collisions. Again, it's not just the number of collisions that matter. There's a lot of collisions that happen, they just bounce off, there's no reaction. You have to still mention, because you have less collisions, the chances of you having favorable geometry is now decreased. Less collisions, less chance of good geometry. Less chance that you're going to have a collision coming in with particles that are moving fast enough and that come in with the right geometry that bonds can break and bonds can form. We're going to need so much extra energy, and I really didn't have that energy to begin with anyways, right? So make sure you know these two features for collision theory here. They always like testing it. You need the sufficient energy argument. Pretty much only temperature can change that. We're at a cold temperature, that's why we didn't have a lot of it, but we have a favorable geometry argument here. It's the likelihood of coming in with the right angles that actually amounts to this. So what I want to do in today's lesson here is I want to just rehash a little bit more with this potential energy diagram. Let's just do an example here. If you remember in our class, we did a burning methanol demo. So basically this one here, we took a big carboy. I took a little bit of liquid methanol, right? It's a liquid at room temperature here. I shook the container, so methanol not only would coat the sides, I'm trying to vaporize. I'm trying to put in the gas state a few of those methanol particles. I know as a gas, those have more energy here. The chances of the reaction to occur is actually faster. Now, question here is for the methanol demo, as I shook up that carboy here, it's not like it spontaneously caught fire. I still needed to spark the fire a little bit. So what's happening here is the reaction I'm intending is still methanol is the formula CH3OH. We're going to react with oxygen because we need to burn it. For a burning reaction here, we're going to completely combust it to form CO2 and water. This reaction here is very exothermic. Combustions are exo, so that means heat is going to be released here. But what you found here, I can have that carboy here sitting in here with all the vaporized, really high energy particles, lots of collisions. How come there isn't any burn? How come the reaction isn't occurring yet? Until what I do is I take a match to it, I take a small flame. That flame there is enough to actually provide the activation barrier to get the reaction going. And if you remember, this is the one that caused a big whoosh down the side. I'm going to plot this out in terms of a potential energy diagram to see what's happening here. For a potential energy diagram, I'll write the word here, potential energy diagram, also referred to as an enthalpy diagram. So if they say sketch an enthalpy diagram, they mean the same thing. For a potential energy diagram here, sure, you can plot potential energy or enthalpy. They use H for it. You can plot it against time, no problem. So sort of here's the early stages and here's the leftover. I'm going to actually prefer to use a reaction. They call this a reaction coordinate. The word coordinate just means an axis. So along the horizontal axis is the reaction. And basically what that allows me to do is, based on the way I've written it, we had reactants on the left, we had products on the right. Well, I would imagine early on I have them all as reactants, later on I have them as products. If I read reactants to products, that's referred to as the forward direction. Turns out a lot of these reactions here that we're talking about are actually reversible. We'll deal with them a lot in the next chapter. Because they're reversible, although I may not be able to go back in time, I can't run the clock backwards. I can just read, well, what if I went from products back to reactants? Reading right to left is now for the reverse reaction. Right? So that's just a little introducing a little bit as we're going to see later on. What is this potential energy? We've been talking about potential energy as the stored energy. This stored energy here is the stored energy in the system. And there's something in the science that says there's too many ways methanol can store energy. There's too many particles. They can store it in between the bonds. They can store it between molecules here. There's way too many ways. I won't know exactly what energy that these reactants have. I won't know what energy the products have. But fortunately for us, what we care is just the change. As the reactants become products, have we overall lost energy? Have we overall taken in energy? In this case here, because the heat term is on the right-hand side, we know this is an exothermic reaction. We know that heat is released to the surroundings. So since I'm plotting the energy in the system, I would imagine my reactants, you can put R if you like, you could even put the chemicals as well. So my methanol and oxygen, they start off at some potential energy. I'm not exactly sure what it is. You can make that note to yourself. Why don't I know this number? There's too many particles and too many ways energy can be stored. Right? But in some sense, I don't really care about that number. All I know is as the reaction occurs, as this burns out to become CO2 and water, it ends up releasing off a bunch of energy. That heat goes to the environment. That's the heat that I actually feel if I touch this carbohydrate from the outside here. So therefore, my system's energy should drop. I should end up at some lower energy reading than before. My CO2 and water, just like before, I may not have any clue what's the exact amount of energy. There's too many particles, too many ways the energy is stored. But I know that steadily I would need to have dropped by energy. I needed to have released off this energy to the surroundings. My system has went down in energy. In grade 11, you may have just connected the dots because what we cared about was a delta H. We just cared about, that we're going to still do this in this chapter. Imagine plopping the reactant line over and then drawing an arrow towards the products. In this case here, you'll notice that my arrow points downwards. In this case here, I'm going to call it my delta H. H revisits here that concept of enthalpy. Enthalpy is another name for this potential energy. If the delta H is actually down like this, the delta H here is negative, which is consistent with the fact that it's exo. Final minus initial, I take a smaller positive number minus a bigger positive number, it's a negative number. What I'm introducing in Chem 12 here is I'm saying, yes, even though the start and the finish are exactly what we did in grade 11, there actually is a little bit more to this. There's actually a little bit of an energy hill between the reactants and products. Now, sure enough, because I already started out higher, the energy hill is not going to be as big as trying to go the opposite way. So, even though this should be favorable, I can make that note here, you'll notice that the products actually have lower energy. Lower energy usually refers to a more stable state, right? Energy is what you need for doing work. If you have no energy, if you're really sluggish that day, not a lot can go wrong. So definitely the product side here is lower energy. I do want to go to that side because it's so much more stable than my methanol oxygen part. But like we saw, even though this reaction here should go to the other side, it should become more stable, it should be able to release this energy, you still saw I actually needed to spark it. I still needed to get it going. What did the spark do? The spark actually gave these particles just that added oomph, just that added little bit to actually get over this energy barrier here. All right? So I'm going to make that note here. Experimentally, why did I do that spark? The spark actually provides the activation energy. It provides that extra push that you need to actually get over the hill. At first, the methanol and the oxygen, the chemicals were all there, but they're not still moving fast enough to actually collide. By having that heat source in, we speed up some of the particles here. Those particles now start colliding. They start exothermically releasing this burn here. They start heating up particles beside it as well, and they just trigger the sort of chain reaction. So the spark provides the activation energy. It provides this energy requirement for the activation energy. I want you to also plop the reactant line over. Always point towards the top of the hill. That arrow, as I've listed for you here, super important definition. We're going to call this the activation energy, or you can call it the activation barrier, EA for energy of activation. They like asking you a lot of definitions in this chapter. So how do you define activation energy? Not only is it the energy between reactants and that top here, you have to mention it's a minimum energy. If you had an infinite amount of energy, of course you can trigger the reaction. But activation barrier shows you what's the least energy you can put in to get the reaction going. So it's the minimum energy to convert our reactants. So convert the methanol and the oxygen in the demo there. Convert the reactants into, they're going to introduce another term. They're going to introduce this term here called the activated complex. For a definition, they will be asking you for these two terms. So define activation barrier, define activation energy. You have to mention the term minimum, and you have to mention the term activated complex, even if you just label it there. So what is this activated complex? The activated complex is actually the species that's sitting at the top of the hill. So that in green there, this is called the activated complex. Sorry, it's getting a little bit messy here. What do I know about the activated complex? I know that it's relatively high energy. We wanted low energy to be stable. This is the highest energy in the whole reaction. This is going to be the least stable. So the activated complex here is at very high, it's the highest energy on the diagram. Highest energy refers to it being least stable. And the reason why it's actually least stable, it's actually in the process of breaking and forming bonds. For a chemical reaction to occur, the electrons have to be rearranged. Let's do the example from yesterday. We had done hydrogen, hydrogen, and chlorine. Those are the reactants. As they become products, they're supposed to look like HCl, HCl like this. Well, the activated complex, which is not I want to emphasize here as well, this is a temporary molecule, temporary species. You cannot isolate it. You can't actually just have this activated complex. The activated complex is actually when the hydrogens have actually run into the chlorines, all 4 atoms happen to be in close vicinity. They happen to be in close contact. And what's actually happening is the reason why they're high energy, they're just starting to break the HH bond, just the Cl-Cl bond, and they're just starting to create this one here. This guy here is called the activated complex. You usually use the equal and the hash symbol to say. This one here is the activated complex. Another name for this activated complex here is a transition state. And they're just trying to use that terminology here, transition state. You cannot isolate this species. You cannot collect a sample where the bonds actually have broken and the bonds are just in the process of forming. You can collect up reactants, the bonds have already formed. You can collect the products after the new bonds have formed, but you cannot collect this transition state here, which is actually the highest spot on this potential energy diagram. So, activation barrier or activation energy is the energy needed to create this guy. This guy here is very high energy, very low stability. It's temporary because it's just in the process of breaking and reforming bonds. Right? So that one there just labels this activation barrier, this EA. That is the EA actually for the forward reaction because I always considered these ones here as the reactants. If I wanted to do the EA for the reverse reaction would similarly take products and actually take them back to become reactants. Going the other way, sketching the reactant line over, we point to that activated complex, we point towards the top of the hill. This one here will actually be EA in the reverse direction. So there was an energy hill that I needed the spark to get over. On the other side here, it's an even bigger hill here. These particles would need to be actually traveling way faster for this reaction to even have a hope of actually getting over. All right? So let me just draw another diagram. It's getting a little bit too messy. We'll end off with this one. So let's do another reaction. Let's do N2. Actually, sorry, let's do it the other way. 2NH3 plus energy becomes N2 and 3H2. This is the reverse of a reaction called the Haber process. Haber, around World War II times, he found a really inexpensive way of taking the gases in the air. Most of our air is nitrogen. He combined it with hydrogen using an iron catalyst. He was able to generate ammonia. Ammonia was used for a really important like industry material for a lot of agriculture, also for a lot of weaponry as well. So it's sort of in honor of him. It's called the Haber process. What I want you to do here is I just want you to sketch a PE diagram. Sketch a PE diagram and label the activation energy. F means forwards, the activation energy R means reverse, and the delta H. So when it says sketch, it means you don't really need to put on the numbers, what's along the X, what's along the actual numerical values. All they want is the trend. So while you still need to label the axes, you would label, well, I have PE on the vertical side. I can even label as H. Remember, H stands for enthalpy. I'm going to label this one here as the reaction axis. Again, the implication is I read left to right, so reactants going to products, that's forwards. This case here, going from ammonia, it actually steals a bunch of energy and becomes N2 and H2. So while I may not know what the 2NH3, I don't know exactly what energy this starts off. I know by the end of it, N2 and H2, this reaction here has been an endothermic reaction. This reaction here has actually stolen heat from the outside, and therefore if I'm plotting the energy, I'm going to emphasize again, this is the system. This is the microscopic particles that are trying to collide here. Those ones there actually are at a hotter condition than beforehand. So overall, by the time you get to N2 and H2, I would expect the N2 and the 3H2, sure, you can just label them as products if you like, but those ones there should be somewhat higher in energy. Again, in Chem 11, you probably just connected the dots. That was fine because all we cared was the delta H. To do delta H, here's your method. You're going to plop the reactant line over. That's my starting. I'm going to point an arrow towards the products. This time, your arrow points upwards. If you did delta H, delta anything means final minus initial. Final minus initial. Well, my final is actually your products. My initial is actually your reactants. Because I'm going a bigger positive number minus a smaller positive number here, this delta H is positive. So that's fine for endo. How positive it is will actually depend on this number here. I think the number turns out to be something like 92 or something like that. This would have to be told to you. So that actually tells you the step size, but we're just sketching anyways, so we don't really need to worry about that. That one would be kilojoules per mole. What I'm introducing here is, even though we are starting from the more stable state, right? We're at the lower energy side. Even though we know the reaction wants to get to a less stable state here, a higher energy, that already required some energy input. Even for this diagram here, there is still an energy hill, and the energy hill is even higher than what the product line would have been. So at this point here, I can actually label the EA forward. The EA forward is from the reactants. Forward means left to right, pointing towards the top of the hill. EA is always a positive value. So this is EA in the forward direction. What's EA in the reverse direction? Well, my reverse direction, I actually don't have as much of a trouble here. Well, I'm already yay high in terms of energy. I'm going to still point towards the activated complex. And this one here will now be called EA reverse. And if you just look at these arrows here, we actually get a relationship. If you like formulas here, you can say, well, my EA forwards, it's this entire black arrow here. My EA forward is actually just a combination between the other two arrows here. It's a combination between doing delta H first, and then a combination with doing EA in the reverse direction. Right? So you have that relationship as well. I usually find it's easy enough just to draw the picture, so I really don't need this formula at all. Even for an exothermic reaction, it's exactly the same relationship, but you just need to be careful this delta H is actually negative when you actually punch it in, because that gap there would actually be the same with the forward activation barrier would be the same as a reverse activation barrier there. Right? Let me make another comment here. In this case here, when we do this potential energy diagram here, we've talked about activation energy. This is the minimum energy that you need to end up forming this activated complex, this high hill here. This one here, actually, when you draw this diagram here, it already assumes good geometry. Remember, for collision theory, we needed to have good geometry and we needed to have enough energy. The enough energy is basically, I need to trade enough energy, I need to get to this top, I need to have a chance of actually reacting. If I have bad geometry, remember, I need extra energy to actually twist the molecule. When I twist the molecule here, that's an added energy requirement. A bad energy requirement would actually look like, let's compare this blue hill, that's the good geometry case, let's compare it to the bad energy geometry here. It's just going to make the activation barrier even higher because you need an extra energy to rotate particles in the bad geometry case. So it's not impossible for a bad geometry case to actually react, but it just means those particles need to be moving even faster. Right? I already have a hard time. I don't have enough particles moving fast enough, but those ones there will actually have an even bigger energy requirement. This is one of the 2 times that the activation barrier is actually different. We're going to see you can change temperature, you can change pressure, volume, you can change all that. It doesn't change the size of this barrier. This is the one time if we compare bad geometry and good geometry, and another time when we talk about catalysts towards the end of the chapter. Right? So have another look over your problems. Just let me know if you have any questions. Thanks, guys.